So last time we talked about constructing the naturals. So we constructed the naturals n and defined them via the Peano axioms. And yeah, so we used the Peano axioms to construct the naturals, and we showed its importance with everything we're gonna do here on out, especially here in foundations. So for today's lecture, we will be constructing the integers and the rationals. So today, construct math BBZ and math BBQ. And why exactly we want to construct them. So if you recall from algebraic femboid theory, this is part of the reason why we need to construct it. That's one reason why we need to construct Z and Q. Because if you recall from algebraic femboid theory, we use the integer Z to be the fundamental group of the femboid torus, or at least just the torus. T2, and for a torus with n holes, we have for it a fundamental group of Zn divided by 2. Z to the n divided by 2. Say if I have a 4, I have a genus 4 torus. I have for it the fundamental group Z. Z2, if the fundamental group is of course abelianized, the original one would, or of course, be a free group in n variables. And that's not original abelianized, we just abelianize it and it becomes Z to the n over 2. Okay, so, right. That's one reason why we want to construct the integers. And that we can correspond every person in a p-space. So every p sub I inside a p-space S, I can make a bijection between p sub I and the integers, or S with the integers. So I can correspond it with the respective integer. And because the fundamental femboid space F is a subset of S, or at least is a subset of C, math BFC, or the fundamentals of all characteristics, then it follows that there is also a bijection between F and Z. So there exists a bijection B that goes from F. I know it's a very boring name or very boring symbol, but it works. And there's no ambiguity. So there's a bijection between F and the integer Z. And the reason why we want to construct the rationals is because combining all of these together would give us the reals, or the real numbers, or by some other extension. These guys are subsets of the reals, and what we're doing is leading up to the construction of the reals. Okay. So let's start with a definition. So we're going to construct the integers, or the construction of the integers will require a little bit of brain work. It requires to define something, and that is called an equivalence class. An equivalence class of an element which I will call A, denoted by square bracket A closing square bracket, is the set of all elements such that, so all of these elements can be denoted as B. A is comparable to A, of course. A is comparable to B implies B is comparable to A or is equivalent to A. And if A is equivalent to B and B is equivalent to C, this implies that A is equivalent to C. And by this law, C is equivalent to A. So, if I'm not mistaken, that's an equivalence class. Just confirm that real quick. Yeah. So these are basically things or elements that are similar to A, in which way there is a bijection between them. So I mean, not really bijection, but there is a quick way of us of representing one as A without doing some external operation. So let's say for the integer 1, or the symbol 1, the symbol 1 over 1 is an element of its equivalence class, or equivalence class of 1. Or let's say for an element, let's say for an element maybe 1, 2, we can say that, I suppose 1, 3 is an element of its equivalence class. So these are strict relatives, or the set of strict relatives of this element A, or this element. This is just the set of all of them. So that's an equivalence class. I know this is a very narrow definition, but what we want is just the definition in order for us to do the construction. Okay, next, what we want to do is define another thing called a quotient set. A quotient set. A quotient set a quotient set, okay, given a relation R, so it could be a binary map on a set X. The quotient set, so this isn't precisely the definition of a quotient set, but it is somewhat of a primer, I'd say. So it's the definition of a quotient set with respect to a relation. So it's not precisely a quotient set. So a quotient set is a very broad term. It could be, mod, like Z mod R gives S1. It could be just regular modulo, like integers mod n, or it could simply be division between two sets, such that I have a set A and a set B, and then I just divide their elements. But we will make this definition with respect to our topic today, which is, of course, equivalence classes. So this is a quotient set with respect to an equivalence class, or with respect to this relation R, or equivalence relation R. So the quotient set X by R is the set of all equivalence classes with respect to R. So the set X gets mapped onto X by R. So that's what it is. So the surjection, so we have a surjection X that gets mapped onto its equivalence class for any X inside big X is called the canonical projection, or canonical surjection. So we can not only call this this mapping from X onto its equivalent, or the set of all equivalence classes of its sets or of its elements, just that, quotient set, but we can also call it the canonical surjection of every element onto their equivalence class. Okay, so there. Quotient set with respect to an equivalence relation R. So it's not really that broad. It's a bit narrow because we only have so much notions of quotienting stuff. I mean, quotient space. We have quotient map. We of course have modulo. But nonetheless, these things here are sort of equivalence classes in the way wherein elements are sort of similar or are related by some relation, right? Some direct relation, but not really a map or a function that you're required to be reversed, like how we wrapping around and gives us, a modulo or implies some modulo, and modulo is an equivalence relation as well. Okay, so quotient set. Okay, so now we have these two definitions at hand, let's go ahead and construct the integers. And then after we construct the integers, we will construct the natural numbers. So here's the clever part on how to construct an integer. And it's not what you think it is. It's not just us basically saying, all natural numbers that have a negative counterpart and stuff like that. Because right now, natural numbers are only positive. We only have 0, 1, 2, 3, 4, dot, dot, dot. How the heck do we extend that to have negative versions of themselves, such that when we have addition, it can be a group, basically, an additive group. So here's the clever part. So what I'm going to do first is take the Cartesian product of n with itself. So I'm going to so if I have a quadrant or I have an axis, a real axis, I'm going to take the first quadrant of it and only consider the natural numbers. This is n. And then this is n. And all of these are just natural numbers. So I'm going to start with 1, 2, 3, 1, 2, 3, and then that just goes on forever. So for a pair over here, so I'm going to replace these over here as with pairs 1, 0, 2, 0, 3, 0, and then on and on. And then here, this time, this is the y. So this is 0, 3, 0, 2, and 0, 1. And then now I'm going to make a bunch of dots that corresponds to some points here. So this is 2, 2, 1, 1, 3, 3. Then right in between them, more dots. Yeah. Okay, so that goes on forever. So we have a lattice of points. Now, what I'm gonna say is that the line, well, all of the pairs that pass through here. So let me try to make it more symmetrical so you guys can see the picture better. Okay. So now I'm gonna make a line that goes through this one. I'm sorry if it's a bit crooked. So 1 plus these. There. Oh no, it doesn't go through that central point, I think. Oh no, it does. It does. Now I'm gonna break it. Okay, and then from 0, 0, we'll also go there. And this is part of the reason why 0 is part of the integers, because we primarily constructed from n, and that we also consider its equivalence class, not just the equivalence class of every number aside it. Okay, and then you do the same thing for the other guys. So make a line that passes through them and the points. Then I'm gonna break it so that it's dotted. And then it goes on forever. So we have an infinite string of lines, or well, imaginary lines, or yeah, non-existent lines, but you imagine that they're there. And these lines are precisely the equivalence class of the corresponding pair where it intersects with. So this line over here is precisely the equivalence class of 1, 0. So all relatives of 1, 0, such as 1, 1, 2, 1, 2, 1, 3, 1, 4, and on and on and on. So we have a step there. So this over here, this line is the equivalence class of 0, 0. And then the line that's over here is the equivalence class of 0, 0. And then the line here is the equivalence class of 0, 1. And then equivalence class of 0, 2. And then on and on and on. And here's the clever part. What we do is define each integer as these equivalence classes. So we define the equivalence class starting from 0, 0 to be precisely the symbol 0. The integer 0. And the equivalence class of 1, 0 is precisely the symbol 1, integer 1. And then the equivalence class of 2, 0 is precisely 2. The equivalence of 3 zeros, you know. Generally, the equivalence class of n, 0, is precisely defined to be the integer n. Okay. And then, for the y-axis, that's what we define to be the negative integers. So for the equivalence class of some pair 0n is defined to be minus n. Z. So the equivalence class of 0, 3 would be minus 3. The equivalence class of 0, 4 would be minus 4. The equivalence class of 0, 364 is minus 364 in the integers. And there, we're practically done. But the last thing we need to do is construct a set of all of these. So this is not really the set integers, or not the entire set, but it is the quotient set of this here, of this string n cross n, with respect to our equivalence class here, our equivalence relation, which are basically these equivalent classes. Yeah. Okay, so the real integers, so finally, z is defined to be n cross n mod this, because this here is an equivalence relation, and that it shows us that for some n 0, it is equivalent to some, under the equivalence class of this here, under the equivalence class of this this pair, this is equivalent at least to some n m, or 0 plus m. And that 0 plus m would just be m according to the Peano axioms, which we've already shown and asserted, because we're using those to construct our sets. So n0, that would be some m. There. Yeah. And then some 0 n, some m n. And under the equivalence class of this and this would become some n here, n integer, an integer n and an integer m, or minus n, sorry. So that would be equivalent to some n, integer n, so equivalent by definition, to some minus n. So this is the actual set here. And of course, because we have some n here, we would imply an equipping of this set with addition in order to, to carry on the structure of n. Because when we do construct a set out of another set, we carry on its structure. I mean, of course, we can make a set without carrying on structure, but as far as we know right now in mathematics, when we construct something out of a set, no matter what our operation is of constructing the set, let's say tensors, direct sum, or tensor product, or some stuff like that, or tensor operations, or linear transformations, or things like that, we preserve structure right now. So yeah, in some way or in many ways, the structure is preserved. Like how I have a set R and then I make a bijection from R onto itself, say a function like x squared. We still have the notion of addition inside it, so we can add two outputs. Let's say if I input 2 into our quadratic function x squared, we have 2, right? And then I have another quadratic output, which is 3 squared, which is 9. I can still add those two and then get a result 11. 13, which is still part of the set, so it's closed, and so it still preserves structure. Okay, so likewise here we preserve our structure by maintaining addition, and assume or imply that by constructing z, there is also a notion of addition between these integers. So that would just be, I suppose, adding the equivalence classes together in order to result in a new symbol. So if I add these two together, if I add these two equivalence classes together, so this is our way of preserving addition. So if I add these two together, 0n, it would result in some equivalence class or element of the equivalence class of 0. So it checks out. So equivalence class, so it would result in the pair 0 and n, which is an element of the equivalence class of the pair 0, 0, which is defined to be the integer 0. And it checks out that this is n, and this is minus n, and we know intuitively that negative plus and negative would give 0 value if these are the same integers, and these are the same integers indeed, so it gives a 0. It checks out with our notion. So that's our way of carrying on our notion of addition. Or we could say that these are not equal. So I have some n, 0, and then I have some m, 0, or equivalence class at least of these things. And then that carries on, or implies to be just n plus m. The integers n plus m. So if I have the equivalence class of 3, 0, and then I have the equivalence class of 4, 0, we end up with the equivalence class of the pair 3 plus 4 and then 0 plus 0. So that's 7. 7, 0, which is the integer 7. And by definition, this is 3 and this is 4. 3 plus 4 is 7. And if it's a negative this time, let's say I switch 0 and m. So n 0 plus the equivalence class of 0m. That gives us nm. So n plus minus m. By definition, swapping this will give us a negative integer, or swapping the order of this order pair will give us a negative integer, for the symbol at least. So that gives us n minus m, or the equivalence class of the integer, or the order pair n minus m and 0. And this would be, let's say that n is 1 and then m is 3. So equivalence class of n equals 1 plus the equivalence class of 0, 3 would give by definition 1 minus 3, which is minus 2. Or the equivalence class of 1 minus 3, 0, which is 2 by definition of our construction. So there, we preserved addition as well. And there's our notion of addition, carrying on over and checking things out with respect to our definition. So there, we have constructed the integers, and we have now established two sets. We now have n, which is constructed by the Peano axioms, and then z, which is defined to be the quotient set of the Cartesian product of n with respect to itself with the equivalence relation. Now let's construct the rationals Q. So what is Q? Alright, so we're practically going to do the same procedure with Z here. So if you guys don't know what Q is just yet, Q is just the set of all fractions. So 1/2 is part of Q, 2/3 is part of Q, even 3/1 is part of Q. In fact, that is an embedding of the integer 3 into Q. So Z and N are subsets of Q. That's one crucial thing that we want to know or want to show. Z, which is a subset of N, which is a subset of Z, is also a subset of Q. Because Q is composed of integers that we stack them on top of each other, which are fractions, right? Now, we won't construct the irrationals just now, but I do think that they are also part of Q because oh no, not really Q, they're not part of Q, there's some different subsets, so we're going to construct those some other time. So, as I said at the beginning of the lecture, we will construct all the sets and then define the real numbers as a union of all those sets. So we're leading up to the construction of the rationals. And along the way, we might prove that some numbers are irrational, like the square root of 2. I mean, this is foundations after all. We are making the bedrock of everything that we're doing in this department or in these courses concerning mathematics. And we will do a full-fledged discussion on ZFC, okay? Because the last few discussions about ZFC were a bit scattered and not really organized. So we will reorganize those lectures and we will discuss ZFC in a proper way. And if you're watching this video or this lecture now after we've done that, just disregard what I said. Okay, so this will require a little bit more work, So we will do this in 3 steps, but it will still involve some more equivalence relations, but we will define a new operation called times or multiplication. So up until now, there is some notion of multiplication between naturals, but it cannot form a magma, so to speak, just yet, because there is no such thing as a multiplicative inverse now, not yet. For some natural number n, there does not exist an 1 over n such that, you know, n times 1 over n gives 1, which is our identity with respect to multiplication. There's no such thing as this yet, because this is a rational number. It's a fraction. And so far, we have no fractions that exist within z and n. So what we're going to do for the rest of this lecture is precisely construct n such that this operation would be defined. And so, in combining these three, we would end up with a magma with respect to m. Okay, with respect to m. So we're going to construct all the rationals in order to define, or at least create a groupoid, or maybe even a group, with respect to multiplication. Because thus far, we're only able to construct a group. We can construct a group out of this and this, and I mean just an integers. We can construct an additive group with this, because we already have negative versions of the numbers. We have negative symbols with respect to the symbols we have. And so we can combine them together to get an identity element, which is 0, right? Because 0 plus any integer would give just those integers. And so we have a group with respect to addition. Now, what we want to do, or the reason why we want to construct the rationals, another reason why is because we want a definition, or we want a way for us, or a place wherein we can construct a group out of multiplication this time. So yeah, okay, carry it on. So we'll do this in 3 steps. The first step is to do exactly what we did to n with z. So first thing is take the product between z and z. So now, because z contains negative versions or negative symbols, we have a full axis, not just one quadrant of an axis. And in fact, when you guys work with simple arithmetic, or graphs, you know, graphs that are discrete graphs that are non-decimal, this is where you're working with. So if your teacher, our teachers back in elementary used to talk about discrete graphs, like how discrete graphs of functions, right? This is where it happened back then. But of course, the entirety of mathematics up until this point exists in R2 or R3. You know, unless you've discussed topology wherein we've discussed Rn. Okay. Alright, so z cross z. Oh, by the way, we will take away 0. We'll take away 0. Because if we do allow an inclusion of 0, that would imply the string m over 0, which is not defined. At the moment, at least. But later in the course, when we do define a ring, I mean not a ring, I mean a wheel algebra, or when we do discuss about, I already mentioned what a wheel algebra is back in femboid theory, but if we do define that, or a projective plane, or the Riemann sphere, we will be able to define m over 0. But at the moment, we don't want that to happen, because that leads to infinity, and infinity is not part of our sets, because it breaks our notion of addition and multiplication. I know that all of these values approach infinity. There is an arbitrary, there's like numbers after each number, it carries on off to infinity, but ultimately infinity is not an object inside our set. So in set theory, and especially here in foundations, we will treat infinity as an object. So it's not a notion of numbers or values getting arbitrarily large, but as we called it in calculus or in Reggie calculus, but it is an object. We treat it as an object here. But right now, we don't want to include it right now because it breaks our rules. Okay, and we don't want that to happen, so right now, we remove 0. So we take the Cartesian product with z and then z without 0. So there is no origin. And you guys will see why we did this later, when we define the actual, you know, division of those, or actual construction of the set. Okay? So this is defined to be the set of all equivalence not really equivalence classes, not yet. All pairs mn, such that m and n are integers and n is non-zero. Okay, so that's our first step. We made this. And you can already see, we can do the exact same thing as we did with the integers a while ago. So if I have a pair here, and 0, and then and 1, 1, 0, 2, 0, and then dot dot dot, I can now make an equivalence relation, but this time it crosses through. And then we have these lines now, just like last time. Right? But we have to take into consideration the minus parts. So it's right over here. And when you visit the Wikipedia page for this, or any textbook that constructs this, it will show something or an image that looks like this, or at least something that looks like this. So it spreads out like that. So something like that. Okay. And the equivalence classes that are represented by those lines are precisely our rational numbers. So now we will define some relations between some of these. So if I index these guys by m sub I and m sub n, so I'm going to index this mn by I. So it will become mi and ni for some I element of integers. And that if I is negative, this corresponds to a minus integer or a negative integer. Okay, and then it's in the left part of our axis, or the lower left part of our axis, so the third quadrant of our axis. So there. So we index it by some element I in Z, any element I in Z. And so we will establish the following relations. So we will define the equivalence class now, or we will define the defining operation or the defining equivalence relation between elements in the equivalence class of this arbitrary ordered pair. So sum M1 and M2 is related to M2 and N2. Oh, M1, N1, N1. If and only if this operation is defined. So we're now defining multiplication, and that would precisely be M1 and 2 is equal to M2 and 1. And this is a crucial rule, because note that, okay, I have a rational number 1/2, and that's not how I'm going to justify it, because we don't have that yet. That doesn't exist yet. Okay, so we're just defining some relations between these integers to show that they're related, and we will also preserve addition, just like a while ago, via this relation. So addition and multiplication in the rational is defined as such. So that would be M1 and N1 plus M2. N2 is equivalent to M1 N2 times plus N1 M2. And N1 times N2. And then multiplication is this binary relation, M1 N1 times M2 N2 is equivalent to M1 N2 N1 N2. So there's our notion of carrying over multiplication and addition, and this is the defining relation between members in the equivalence class of this. So finally, we define Q as the quotient set of this set and the equivalence relation. So the set of all equivalence classes of this arbitrary ordered pair. So now I can replace this. So finally, Q is defined to be Z Z cross z without 0, z cross z without 0 mod equivalence relation, which is defined to be the set of all equivalent relation Nm such that Nm is in z cross z without 0, and that m is not equal to 0. And each of these equivalence classes is defined to be the symbol n over n, or n over m. Yeah, n over m. So now, the equivalence class Nm is defined to be the symbol n over m. And that is the reason why m cannot be 0. And that's why we extracted 0 from this one over here. Because we would end up with an n over 0, and that's not defined. Right now, at least. And don't want to concern ourselves with defining it, because when we do define it, it breaks down the algebra and everything. So there. That's how we constructed the rationals. And as you saw a while ago, we did preserve structure and introduced a new operation, which is multiplication. So what now is our, how do we preserve our operation? What's our operation, what's the operation we get when we add two rational numbers and then, switch the stuff, right? So if I have two equivalence classes of varying order pairs, right, what would be our resulting addition? So I will replace my marker with a better one, and we will continue. Okay, so alright, what is our defining operation in? So what happens when we add these two? So you recall from elementary that n plus m. So I'm going to denote another equivalence class, AB. And then I have, yeah, n over n. So this is n over m plus AB, sorry, AB not AM, which is equal by definition to adding of these two equivalence classes. And you'll see a while ago why I defined those relations. So nm plus the equivalence class of AB, and you will see that it is, if you recall a while ago, it is precisely the equivalence class of n times n2, which is B, plus n1 times m2. So that is am. So am, and then that is n1 times n2, so m times b. And that checks out with our intuition that this over here, this mixed or addition of two fractions with varying denominator, gives us nb plus am over m times b. Or if I use AB and CD, A over B plus C over D gives us, use the fish method, as if this is packaged in a matrix, A times D plus B times C. AD plus CB, or BC, over B times D. And check that out with a bunch of integers, and it checks out. That is exactly what it is. And you can reduce it, of course. It's possible, given our multiplication rule. That's exactly why I defined it like this a while ago. Why I defined the addition operation like this a while ago. Because when we convert this into its corresponding symbol in Q, which is n over m, or nb plus am over mb, we realize that the rule holds for what we thought the addition is, or what we think addition works over fractions. I know I hated fractions back then, but this over here gives me a new perspective.
by constructing it itself. It's like making a child, and then thinking before that having a child is too stressful and stuff like that, and then once you do have a child, oh, the joys of creation. It gives you a new perspective in life. I know it's sort of a horrible analogy because this year doesn't cry or poop all the time or shit or stuff like that, but it works the same principle. Once you construct something or see something from the ground up, it really gives you a new appreciation for it. So yeah. So thank you for bearing with me up to this point. Now how about multiplication? So I defined multiplication a while ago as m1 times n2 and then n1 times n2. Oh, actually that's m2. I think that's m2. Yeah, that's m1 times m2. So really the definition of, so if I have AB and then I multiply it by some equivalence class of CD, integers of course, that gives me AC BD. Yeah, that's supposed to be it. Because once we do the multiplication of the symbols A over B times C over D, that should give us AC over BD as we intended it back in elementary. And so it checks out when we multiply them, it should do that because this is AC over BD in symbol form inside. Once we do the map of corresponding this equivalence class to a symbol, like we did with the integers and the natural numbers, or natural numbers with the integers, it checks out. So yeah. So showing this in symbol form would give us, so the equivalence class of AB times the equivalence class of CD is by definition A over B times C over D, which is AC over BD. I mean, it's commutative, but yeah, it's pretty commutative. And that is precisely the equivalence class of AC times BD, which checks out with our intuition or our definition of this in our intuition that is how fractional multiplication works. Okay, so just to check out real quick why exactly we end up with a group with respect to multiplication. I have n and m here, so okay, I'm gonna erase this here so it's clear. I have n times nm, which is n over m. Now I just flip these two, right? That should give me 1, which is our identity. Because E times A equals A times E is just A. We need an element that gives us just an element inside it when we multiply it by. So under addition, that would be 0, of course. Obviously, you guys already know that. But in multiplication, that would be 1, because any number times 1 would just be that number. So we're gonna show that it would be a group. Okay. So I have, under our established rules, of course. So n and m. Now times that with m and n. Okay. So that gives us the equivalence class of nm times mn. And these things are, and multiplication, as we know it, is commutative. We can swap these two. So not only is it not only is it a group or would form a group, but it would form an abelian group, if I'm not mistaken, with respect to multiplication. Okay, so that would give us nm over mn. But recall that if I have some like this, right, n and then 0, right, and 0, and I multiply it by some 0 and n, that give me some n here and 0 and then 0n. So 0, equivalent of 0, 0, and that is defined to be precisely 1. Yeah. Now that doesn't mean 0 over 0, but oh wait, yeah, it's not 0, but precisely just the equivalence class of 0. So this isn't 0, but it is 1. Because we can think of this as n here. So it's either 0, 0 or n. When n over n is 1. So by this definition, this would vanish because it would cross out to 1. So that's, I guess, our rigorous proof of why this will form a group. And so that 1, which is packaged, or which it comes from the symbol 1 over 1, which is the equivalence class of 1, 1. Yeah, times this would give us just that. So okay, so equivalence class, so nm times the equivalence class of 1, 1 would give us the equivalence class of n times 1 is just n, and m times 1 is just m. That would give us just n over m, which is the same as saying n over m times 1 is just n over m, which is, you know, also equivalent to 1 times n over m. Left and right multiplication work the same way with respect to our current terms. And so finally, yeah, we really did it. I don't have to say it finally anymore. So there, we have constructed the rationals. And so we have 3 of these. Now the rest of the real numbers, it will require some work to construct them, but this is just what I want to focus on for this lecture. So finally, you can say that Q is equal to Z cross Z without 0 mod same equivalence relation, this one. So there. And so yeah, Q over here, Q would imply both addition and multiplication, and it won't precisely be ring. Oh, I haven't defined negative versions of it yet. So basically, negative version of, if I have some equivalence relation of a pair A, B, its negative counterpart, so A over B, its negative counterpart would just be switching A and B. It's so, because we constructed the integers by defining a swapping of the first, you know, equivalence classes of those base points, you know, like 1, 0, 2, 0, 2, to be negative, right? The equivalence class of those to be negative or positive or negative respectively. This time we do the same thing but swapping it. So the equivalence class of A0 would be precisely, or by definition, be minus, 0 cannot be negative, so let's be, so by definition A over B, but the equivalence class of BA is precisely minus A over B. Okay. Or rather 0. No, it can't be 0 because, you know, we took 0 out. So for those two integers. So adding those two together should by definition give us A0. Right? And for differing denominators, it's defined to be just a, we know that it is AD minus BC over, you know, D times B. AD BC, or yeah, DB. And you just swap the operation while ago with just negative. So we're multiplying with negative symbols, or we're operating with negative symbols. So add by the negative symbol. And, you know, thus the negative version or negative counterpart, or the inverse map of that symbol with respect to, you know, our equivalence relation or construction of equivalence classes. So there, we finally have the rationals, and this is a good place to stop.